Hello everyone and welcome back to the second week of labs. As promised, this is the pre-lab video. And so what we're going to do here is essentially just go through this lab document. I'm going to show you how to actually essentially do what you're looking to do in this. So for our lab today, we're going to be looking at a data set which looks at a combination of different antidepressants that might cause anxiety. And so the dependent variable here is anxiety, going from 0 to 20. And what you're going to be asked to do is test the assumptions and then test for the main effects. Now here I just have some more specific instructions for you. So there's going to be a chart for you to put in those assumptions and what you're finding. And then I'm going to ask you to decide, are the assumptions met? And if they're not, what should you do? And this might involve you making a change to the data set, which would mean once you make a change, you always have to reevaluate the assumptions to see if now they're met. After all this is done, you can test for those main effects. So here you're looking for significant results. So either the main effects, interactions, and that overall F value too. And what if there's any significance, what do you think is driving those effects? So I want you to use some post-hoc tests to figure that out. Finally, I'm going to ask you just to write a really brief paragraph reporting those findings. This isn't something that you have to hand in to us or anyone, but we found in previous years that students get really confused about how to actually report statistics. So we're going to try and incorporate that into lab. And so have you not just run the statistics, but make a little write-up just so that we can say, okay, here's how you definitely want to do it. Here's maybe some tweaks and how you're already doing it. And so that'll make it a lot easier once it comes time to write those topic assignments. Okay, so moving on to the data. This week, we're not giving you a data set. Instead, we're giving you the data, and the first step is that you have to actually put it in to SPSS. So here, you see that step 1 is input the data into SPSS. So really what you probably want to do to start here, let me change scenes, there we go. What you want to do here is we're going to go over to the variable view. If you see here, there's two different drugs, so drug A and drug B. So I'm going to put in here A, and then I'm going to put here B. Both of them are numeric, sure. I'm going to label this as drug A level, drug B level. Values, I might want to put, okay, so we see A1 is no dose, so I'll put 1 no dose. 2 is low dose. And so on and so forth. And then we're also going to need another variable for anxiety. We were told that this is anxiety. Now this is also numeric, and it's fine to have it like this. You might want to change over here the values. So this is measure. So is it scale, ordinal, or nominal? Both drug A and drug B are nominal. That means that there's no significance between the values, right? But for anxiety, this one would be considered scale because, well, we're assuming that there's some significance, and the difference between 4 and 5 is the difference between 5 and 6, and so on. And so that means that we're dealing with scale data. So once you have all of this put in, you can start inputting this. So A1, B1, and then anxiety of 5, 7. So you're copying these down. Another good idea is to create a column that represents participant numbers. So I might go here and say, okay, I want to insert a variable before this. Let's say this variable is going to be P number. Can I do that? Yeah, so this is participant number. So I'm just going to number this all the way down. There's actually a command that you can make do this for you. I just forgot what it is right now. So first step is actually enter all of this data into SPSS. I'm going to ask you to pause the video here and come back once you've got it all entered. Did you pause? I hope so. So here is what I have now. So like I talked about, we have an ID number, we have drug A, drug B, and anxiety. We did this step 1 of inputting the data. Now it's time to test the assumptions. There's a number of assumptions for ANOVA, but for our purposes, there's really only 2 that we need to test. And you'll get more of a discussion in either your PSYC and Stevens textbook or the Tabachnik and Fidel textbook. And essentially, we need to test for assumptions because, well, what we're running kind of relies on a couple assumptions. And if they aren't met, then we can't really trust our findings. So here we have the steps that you'll need to go through in order to test these assumptions. So going back to my SPSS, I can see, okay, I need to go to Analyze, Descriptives, Explore. So we're going to put these in the factor list for right now. Anxiety, so move over IVs to factor and anxiety to the dependent. Now we're going to want to click on statistics. We want the descriptives. And in plots, we want the histogram. We do not need the stem and leaf. We want the box plots. And we want the normality plots with test. After all that, we're going to click paste. So after we paste that, it'll give us syntax looking something like this. I can highlight it all and click run. And it's going to give me output that looks something like this. Here we can see, okay, separating the sample by drug A. So looking at all of the no doses together, all of the low and all of the high. So each one of those things separate. We can see the descriptives. You can see these are what you'll be wanting to evaluate. There's the Shapiro-Wilks test, the histograms, the box plots, the skew, kurtosis, and a preliminary assessment of variance. Now, you can see we have this separated by drug A, and then we have it separated by drug B, but that isn't everything that we need, actually. If we go back to this data, that's giving us all of these averaged together and all of these averaged together, right? But when we're doing an ANOVA, we actually need normality for each cell. So it isn't enough to look at the entire group and see if it's normal, or look at one main effect and see if it's normal. We actually need to look in just an individual cell. Is this cell normal? And at each individual one. So to do that, it's going to be very similar to what we were doing already, but here we want to actually split the file first. So I'm going to go back to the data set, go over here, data, split file, hit compare groups, and put drug A in there. And we can paste that, get this syntax, which you can then run, and now we'll have the data set split. Now we can rerun this, but since it's already, the data set's already split by drug A, I'm actually just going to remove drug A from there. We don't need it. It's already comparing by drug A. So I'm going to just run all of that again. Now up here, I'm getting way too much output, so I'm going to just minimize the output from before. And here we go. Here we have the descriptives for each cell. So not for each main effect or anything at this point. Now it's each cell. When we look at this, we have the instructions for you written here already, so I'm not going to spend too much time on it. But I'm just going to quickly look at one of these for each. So Shapiro-Wilks is the first one. And so for that, we scroll down to these tests of normality. Now you see we'll get both the Kolmogorov-Smirnov and the Shapiro-Wilk. Because each cell has less than 50 observations, we're going to use the Shapiro-Wilk. If it has more than 50, we would use the KS test instead. So these do similar things, but the sensitivity is different, and so they're better for different sizes of data sets. So if we look here at the Shapiro-Wilk, drug A, no dose, drug B, no dose. So again, that would be this specific cell, this first cell here. It's telling us that this test is significant. What does it mean if it's significant? Well, that's bad. We do not want the test that we do for our assumptions to be significant. Significant, that means that there's a significant departure from normality. So right off the bat, this is telling us, there might be something here, we should check it out. Don't worry too much when these tests are significant. Oftentimes, they can be very overpowered. Even with a sample size of only 12, still pretty powerful. And so that means that we're going to see significance, and it's up to our interpretation after that fact to figure out, okay, does this actually matter? And that's why we don't just look at the Shapiro-Wilk. Next, we might want to look at the histograms. So again, for this first drug A no dose, drug B no dose, here's the histogram, and it looks pretty gross. It looks pretty skewed, honestly. And this is because even though this is scale data that can go between 0 and 20, we see a lot of grouping. So here there's only actually 4 values being represented for this cell. And that means that well, this doesn't look much like a normal curve. But that's, again, fairly typical with low ends. So only 12 here. The less there is, the less it's going to look like a normal curve anyways. The next step might be to look at box plots. And again, let's look at drug A, no dose, drug B, no dose. And this is what the box plot looks like. If you haven't read a box plot before, essentially this is the 50% of the data is in this box. The middle is the median, I believe, and then the whiskers are the most extreme scores. You might also notice that we're not looking at it right now, but this drug A no dose, drug B low dose has this up here. That means that this is an outlier, so you can see the next most extreme score is here. So a box plot can also be useful in kind of telling you when there's a possible outlier. So here, looking back at this drug A no dose, drug B no dose, this looks pretty good. It's missing the whisker on this side, but overall, the median is in a good spot here. The box, like right in the middle of the box, the whisker is a good length for the box. Just looks pretty normal. It's not wildly skewed. So the box plot actually looks not bad. Next up on our list here, we have skew. I'm going to just go back up here. So here again, drug A no, drug B no. So for that, we want to look at these values, skewness and kurtosis. Now, different people have been taught different ways of evaluating these numbers. What I was taught and what we're going to have you guys do is essentially you're going to divide the statistic by the standard error for that statistic. So here, if we divide 0.57 by 0.64, that's going to give us a value around 0.9 or something, 0.8 or 0.9. And what that gives you actually is a z-score, right? Anytime we divide a value by its standard deviation, or in this case standard error, that's a type of z-score. And once we have it as a z-score, that means that we can evaluate it on a normal curve, right? So z-scores are just telling us standard, how far away things are to the center of a normal curve, and should they fall that far. So here, we're not seeing any problems, because the z-value for this skew is 0.9. And if you remember a normal curve, we expect 95% of the data to fall within plus or minus 1.96. We expect 99% of the data to fall within plus or minus 2.5. And we expect 99.9% to fall within plus or minus 3 or so. And so here, the value is well below any of those cutoffs. For skew, as it says here, we're going to typically just use the cutoffs of plus or minus 3 for these z-scores. And again, that's just because that gives us a very liberal cutoff. Next, we might want to look at the kurtosis, right? So skew is how normal it kind of looks between things being on one side more than the other. Kurtosis is how high up that goes, how well spread out the values are along that distribution. So here we can do the same thing again. So I'm just going to divide this kurtosis statistic by the standard error associated with it. And if I wanted to show my work, I could do the math, but I can also just say, well, the statistic is smaller than the standard error, so I know that this z-score is going to be below 1. So I know that it's fine. Will it always be fine? No, definitely not. So again, we can just look down at drug A no dose, drug B low dose, and see, okay, here the skewness, we would have to actually do this math, and we'd find out that it's slightly below 3, but pretty close. And the kurtosis here, if we did the math, we'd find out that it is above 3. So looking at skewness and kurtosis for this cell might tell us it's not looking very normal. It looks like there's some significant departures from normality based on the skew and kurtosis. Next, we're asking for the group variance. So this is just a kind of preliminary way to look for next assumption that we haven't talked about yet. Everything we've done so far has been about normality. But another assumption we need to test for ANOVA is homogeneity of variance. And what that's saying is the variance of each cell approximately equal? And this is important because when you look at the way the ANOVA is actually scored, all of those variances are pooled, which means that if one is wildly larger than the other, that's going to be a problem. So up till now, we're looking at a normality within just one cell, but now we have to compare cells. So how we do this is we can look here, and I can see, okay, variance, this one is 1.09. And just looking down at the next one, okay, this one's variance is, 11.1. You can see here, you want the group with the largest variance to be less than 4 times the size of the smallest group's variance. So essentially, you can times the smallest by 4, or you could divide the largest by 4. Here, we'd want it to be less than 4.16, right? But here, I haven't even looked at all of them, so there might be more egregious cases. But here we can already see, just between these two, this is a difference of 11 times, almost. And that's probably going to mean that there's a problem with this homogeneity of variance. There's another thing that we can look at. It's not in this instructions for you because it's kind of harder to evaluate and a bit more confusing for people, and it doesn't, you get enough information from everything else. But just so that you know what it is, especially since we did get it, is these QQ plots. A lot of people get really confused by them. So essentially what this is we're just looking at, so this is the expected normal. So if this curve was normal, what would the scores we'd be expecting be? And then how does that differ from the observed value? So essentially it's just a plot of expected normal versus actually observed. And when you see this line here, this is imposed on there. If this curve was actually normal, all of these dots would be on the line. And so we can use this as a way to say, okay, the further away these dots are from the line, the further away from normality this is deviating. Now, I don't like looking at these normal QQ plots because they are confusing for me. My brain can't look at this and say, yes, that is this far away from the line, therefore, whatever. I can't do that, so instead I like to look at the detrended QQ plots. Essentially, all we've done here is we took that line that was there, and now we've calculated the distance between the dots and the line. So here we can see that for this dot, it's about 0.2 away from the line. The units don't matter exactly, just know that it's pretty close. So here, the furthest dot from the line is about 0.5. What does that mean? Well, it's not that bad. 0.5 isn't too bad from the line. Everything is below 1 at least. I haven't heard of any really hard rules for interpreting these values, but less than 1, it's not too bad, not too big of a deviation. Obviously, the closer it is, the better. So if everything was within plus or minus 0.2, that'd be even better. But you can see, now remember, everything that we were looking at before said that this cell, this drug A no dose and drug B no dose, was pretty normal. So this is kind of confirming that. But of the couple times that we looked in there, we saw that the drug A no dose, drug B low dose, so A1, B2, we saw that this square might not be as normal. So let's just take a peek and see what that might look like for a non-normal cell. So here we can see almost everything is within plus or minus 0.5, but then we have this huge outlier over here. We can see its value is about 1.2 or 3 or something, right? So that's quite high. So you can really see this difference between here, these things are pretty within, pretty what we expect, and here's a large outlier. Now, everything that's non-normal isn't going to look exactly like this, because this one looks this way because of an outlier. So oftentimes you might see something that looks like a big U, or you might see a big line like that, a wave. The U's are typically the more problematic ones. Okay, so that's just if you wanted to look at these QQ plots, that's kind of how you would interpret them. You're just looking at the distance away from the this trend line these dots are, or a bit more easy to see, the distance away from 0 the dots are once we detrend the line. Like I talked about last lab, we need to turn that split file off. So let me just go here, data, split file, analyze all cases, do not create groups. We paste that. All it says is split file off. So again, if you know the syntax, it can often end up actually faster than going through the menus. So now we want to go to Analyze, and we're actually going to run an ANOVA. That's what we're doing here. You might think, wait, why are we running the ANOVA? We're not done with the assumptions yet. And you're right, we're not. But there's some things that we can only make SPSS give us by running the ANOVA. So we're running the ANOVA, but we're not analyzing it yet. We're not going to analyze it, we're just looking at the assumptions. So what we're going to do, go here, analyze, general linear model, univariate. So here, our dependent variable is anxiety, and then we have two independent variables, right? So here we're calling them fixed factors. They're not covariates because that would be an ANOVA, which we have not gotten to yet. So we can look into these things. So if we look at the model, we're doing a full factorial, and that's what we want. So we're looking at all of the different variations between these. Contrasts. This is just a way to do some post hoc tests, essentially. And this is something that you can play around with on your own afterwards. Here, if we want plots, I really like making a plot. So I'm going to put drug A on the horizontal axis, drug B on separate lines. Again, not useful now because all we're doing is testing the assumptions, but I'm just showing you what all the options are. Post hoc, again, this is something that you'll want to run on your own after. Means, again, not something you need right now. You might want it after though. And then save. So here I actually do want to save something. So under these residuals, I want to save standardized values. Now why is that? Well, basically this is going to tell me how far away values are from expected. So a residual just means, again, how far away you are from that expected line. So if we save these standardized just means that they've been converted into z-scores, we're going to have a even more concrete way of saying, okay, this is probably an outlier and probably needs to be removed. So this is something that we want right now. Next, go into options. Options, there's a lot of things that you might want to do in here that don't matter for the assumptions. Descriptive statistics, always useful to have. Less useful now because we just ran all of those things. In running the assumptions, we have a bunch of descriptives, but it can be useful to have it all in one place. Estimates of effect size, always good. We're kind of, stats as a whole is moving away from significance values and moving towards effect sizes. And so it's always good to have that effect size and also the observed power. You know, is this actually powerful enough to do what you want? Observed power is less useful. Typically, power is something that you want to think of ahead of time, but still something. Here, what we want is the homogeneity tests. So if you remember, we looked at the variances of cells and compared them earlier. Now we want to get an actual test for that. So really all of this that we're doing right now is just for this homogeneity test and for these residuals. So now that I got those two, I'm going to paste that. You can see it comes up here, and I'm going to run. Again, I don't like there being so much, so I'm going to just close that. So here we can see this. We can ignore that. That's just telling us, okay, what exactly are we doing? We can also ignore this. This is looking at the actual thing. But this isn't something that we're looking at yet because we're still on the testing of assumptions. So here, you know, it's curious. When we were looking at the actual cell variance before, we saw that it was quite, there's quite a disparity just between the two that we looked at, 11 to 1. But here, this is actually saying that it's not significant. Typically, you will find that Levene's tests will over-identify differences. So a more common scenario is there's a difference between 3 to 1 or so between groups, between the group variances, and Levene's test will still be significant. It tends to be pretty overpowered. But one problem that it has is it's pretty sensitive to normality. And if we have a problem with normality first, well, that needs to be solved before we can do anything else. So again, you know, we're thinking there might be a problem with normality here. And so that might be causing Levene's test to show up as non-significant, even though otherwise it would. Who knows? But regardless, after we deal with normality, we'll have to rerun this and see what it says. We looked at Levene's test. We don't want it to be significant, because if it was significant, that would mean that the variances are not equal. Surprisingly and weirdly, it wasn't significant, even when we looked though when we looked at the actual values before, they looked not great. So that was a mystery. And then we also have these z-scores. Now again, z-scores you can evaluate on a couple different cutoffs. 1.96 if you want a more conservative, 2.5 for a little bit more liberal, or 3 for pretty liberal. And oftentimes what your cutoffs are going to be, especially for outliers, is going to be based on your sample size. Here, we're just going to use that cutoff of plus or minus 3. Here we have the data set. And as you see, it saved these residuals. We want to find things that are plus or minus 3. Now, there's fancier ways to do this that will actually give you an indicator, but a very simple way to do it is just sort it. So here, I just sorted it one way. Oh, and we can see right here, here's something that looks like an outlier because it's above plus or minus 3. If I sort it descending, yeah, here's 2 more that look like outliers. And you might recall back when we were looking at those box plots, we saw one. We saw an outlier that was pretty far away from the standard scores. Now, if I just go back to looking at the scores here, it's actually not that difficult to spy those outliers. Do you notice them? Like here, this one, 17. Pretty high compared to everything else there. Here, 3, when everything else is so high. And here, an 18, which is double the next highest. What we do with these might change, right? So we haven't looked at really everything, right? I just very briefly went over the different assumptions, and I want you to actually fill out this chart. So what is the assumption, and how are we testing for it? And then based on that test, what is your interpretation? So this is just one of those things, right? These z-scores. These z-scores are telling us, okay, there's 3 cases that are most likely outliers, and outliers aren't part of normality. So that's one thing to put in this interpretation section. There's all these other tests, and I want you to actually fill that out because it's very useful. But after you do that, you'll have to think, okay, are these assumptions met? If there's any violations to normality, are they not severe enough that I can continue on? Or do I need to make changes? We identified 3 outliers. What should I do with them? Should I remove them? But there's only 12 observations in each cell, so if we remove just 1 out of that cell, well, that's pretty significant amount removed. But we can't just leave them there. Now, one thing that you may or may not have heard of is Windsorizing. And this is a solution that can sometimes work for cases like these, where we don't really have enough data that we can just willy-nilly delete it, but it's also severe enough that we might not want to keep it. So you can try a couple different solutions, different ways to deal with this, but here's one, since I don't know if you would have thought of it on your own at this point. Windsorizing. No, it has nothing to do with the city of Windsor. I don't know why it was named that, but it wasn't about Windsor. But what you do here is you take that extreme score, so here it's 18, and we say, okay, we're going to preserve the kind of rank order here. So one solution for extreme scores sometimes is to replace it with the mean, right? That's what we do with That's one solution to dealing with missing data. But instead, to kind of preserve that rank order, we might say, okay, so it's 18, so it's higher than everything else. The next highest here is 9. So I'm going to replace this 18 with a 10. Now it's still higher than everything else, but it's not so high anymore. So this is one solution, and you can go back, so fix these 3 outliers by Windsorizing. Here it's not higher than everything, it's lower than everything. So here you would want one step below the smallest, which right now is 16. It's 15. So you'd replace this 3 with a 15. So after you do that, you can go back and re-evaluate those assumptions. So what does normality look like now? What about homogeneity of variance? So this has been a while of me just chatting at you, going over all of this. And so I want to just leave you now to fill out this chart with all of these assumptions, all of these tests. Use what we've given you here and here as guidance, and fill out this chart, and then decide what you want to do about any violations you see, like those outliers. If you want to Windsorize, if you want to remove them, whatever it is. And then reevaluate. Check back in on each of those tests and see, okay, what does it say about these assumptions now? Because they might say something different. Last but not least, the last part here is actually conducting the ANOVA. I'm not going to go over this with you right now. I already showed you how to run the ANOVA when we were looking at these assumptions, so I'm not too worried about that. We give pretty specific instructions here. So yeah, run that ANOVA and decide, okay, what's going on here? Give us a little write-up. Again, you don't have to share it with anyone. It's just for your own benefit. And we will see you in lab next Tuesday after you answer all these questions. In lab, we will go over these things. Were those assumptions met? What did you put in that chart? What did you do and how did it change things? And what did the ANOVA actually say? And how to actually report. So that's what we're going to be doing in lab on Monday. Hopefully this long pre-lab video was helpful in kind of just reviewing this. As I mentioned before, essentially all we're doing with these pre-lab videos is walking you through these lab documents. It's just meant as kind of a help if you're confused or maybe answering some questions that would have otherwise gone unanswered. And yeah, just making sure that we're all ready to spend the actual lab time doing just the interpretation section. So come to lab with these questions answered and any questions of your own that you might have had as you were completing this. I look forward to seeing you all again next week.